Very good. So today we have a special Kadanoff seminar given by Omer Aksoy, all the way from the Paul Scherrer Institute and ETH Zurich, and he'll be telling us about Lieb Schultz Mattis type theorems for Majorana models.
Thank you very much. Thank you for having me. So today I'll be talking about LSM type theorems for fermionic systems with only discrete symmetries. This is a rather older work, but I will also talk about some upcoming work. My main collaborators for both works are Apoorv Tiwari at KTH, Sweden, and my supervisor, Christopher Mudry. So the motivation for studying LSM theorems is actually coming from a very general grounds. One of the questions that we're interested in condensed matter is the so-called spectral gap problem, in which, given a Hamiltonian acting on some Hilbert or Fock space, the question you may ask is there a spectral gap separating the ground state from excited states? And if you can find such a spectral gap, you also want to ask about if the ground state is non-degenerate, or what type of symmetries it has. Now, on general grounds, we know that this question is very hard to answer, but some sort of partial answer can be given by the Lieb Schultz Mattis theorems by constraining the spectra. Now, the original LSM theorem was proved for a Heisenberg spin 1/2 antiferromagnet in one dimension. And the idea was that the system would consist of spin 1/2 or spin s degrees of freedom at every repeat unit cell. And it has two kinds of symmetries, translation symmetry, which I denote by Zn, and the U1 spin rotation symmetry. And the original LSM theorem states that the ground state cannot be simultaneously gapped, non-degenerate, and symmetric under both the translations and U1 symmetry, only if the spin degree of freedom at every repeat unit cell is an half integer. Now, one way to understand this proof is the following. It follows in two steps. So the idea is that let's assume that there exists a gap, non-degenerate and symmetric ground state, and let's construct a variational state. Now, the way to construct this variation state is by using the global continuous U1 symmetry. You construct the variation state by locally smoothly twisting or rotating the angles by a twist operator. And then in the thermodynamic limit, first, what you can show is that the variation state energy approaches to the ground state energy. So this forms the first part of the argument, namely the energetics. And the second part is that you can also show that the variational state is orthogonal to the ground state, only if the spin degree of freedom at every repeat unit cell is a half-odd integer. And this follows from the fact that the ground state is assumed to be symmetric under both translations and internal symmetries, and the 2π rotation of a spin 1/2 degree of freedom gives a minus sign. Then you can conclude that the overlap is 0. And this sort of forms the kinematics parts because it's related to the properties of the local Hilbert space. Then one can conclude from these two steps that the ground state must be either gapless or degenerate at the thermodynamic limit. Now, my plan with this motivation, my plan for the talk is that I'll describe certain type of LSM theorems that apply to fermions with only discrete symmetries, for which such a smooth twist operator does not exist. Actually, they come in two flavors, so I will describe what I call Majorana LSM theorem 1 and 2, and then I will sketch their proofs. And then I will also talk about some upcoming work about systems with LSM constraints and certain dualities that can be obtained by gauging internal symmetries in one dimension. Okay, so let me start with the first part of the talk. So for a fermionic system, if there's a particle number conservation, there is always a global U1 symmetry, and then one can prove if you have a global particle number conservation, LSM type constraints, and in general, such theorems can be summarized as follows. If each repeat unit cell has a non-integer number of electrons in a particle number conserving system, then you cannot have a translationally invariant and a gapped and symmetric ground state. Okay, so this is the analog of a LSM theorem that is for the half-odd integer spin. But what happens if we break this U1 symmetry, let's say in a mean field treatment of a superconductor? So the first part will be focusing on this type of theorems where local fermionic, there are local fermionic Hamiltonians for which there is no U1 symmetry. And I will assume that on general, my global symmetry group is some internal symmetry GF and some translation symmetry. So as exemplified by the spin systems, it has to do with some global local properties of the symmetry groups. So let me first start by some background on the fermionic symmetry group GF, what I mean by this object. So a fermionic symmetry group GF it must always contain a Z2 center, which is the fermion parity symmetry, which must be a symmetry of any fermionic local Hamiltonian, and it must commute with all elements of the GF. So that's what makes it sort of special. And fermion parity symmetry is assumed to be never broken either spontaneously or explicitly. Then, given some group GF, you can define the bosonic part of it by cosetting the fermion parity group, which I denote by GB. And on general grounds, GF does not always have to be the form of, does not have to have the form of a direct product of GB and fermion parity symmetry. In general, there are multiple ways of embedding it, and this is in mathematics what's called a central extension problem. So, for example, a trivial central extension would be embedding what I denote by Z2 is the time reversal symmetry, embedding the time reversal symmetry into the fermionic symmetry group as a direct product, and a non-trivial extension would be getting the cyclic group Z4, where the time reversal squares to fermion parity. So these are respectively the spinless and spinful time reversal symmetries. Now, all my results can be extended for a generic group GF, but for convenience, I will just focus on the case of direct product structure, where I can write GF as a GB times Z2F. Okay, then now the LSM theorems at the end will turn out to be about the representations of this fermionic symmetry group. And right now, my goal will be to just construct a fermionic Fock space on which representations of GF will act. And let's first think about the even number of Myron operators. What I mean by that is that my Fock space is an even dimensional vector space, and every operator acting on this vector space can be represented by the Clifford algebra spanned by these Myron operators. And also I can, of course, out of even number of Myron operators, construct some complex fermion operators, which then span the states in this fermionic Fock space in the usual way. So I assume that there exists a vacuum that is annihilated by all the annihilation operators. Then a representation is essentially a map from GF to the linear or anti-linear maps on the fermionic Fock space F. And in particular, there's a special symmetry, fermion parity, which has a, let's say, fixed representation given by this. Then for the remaining symmetries for any element GB, we can in general represent it as a unitary operator together with a complex conjugation. And here C is a group homomorphism from the group GB to the Z2, which indicates if my symmetries act in a unitary or anti-unitary way. Okay, then a representation of any group actually follows the group structure of the group GB. So what does that mean is that the identity operator is, the identity element is the identity operator, and there's a composition rule. But because of the U1 ambiguity of the quantum mechanical states, I allow for a projective phase to exist. And I also demand the associativity, of course. Now, the question one asks is that, can you redefine your operators U and get rid of this projective phase for a given representation? And there are certain conditions this projective phase must obey. These came from associativity, namely, if you demand associativity, the phase factor nu must obey this condition, which is called the co-cycle condition. And then also each nu is equivalent to some other nu prime under gauge transformations. If I define my representation for the element GB by a phase factor, I must get an equivalent representation. And then inequivalent projective representations are classified by the equivalence classes in the second group cohomology. So the enumeration of the phase factors nu that obey the co-cycle condition up to this equivalence relation are called are enumerated by this object, which is the second group cohomology. Okay, so with this mathematical background, there is one more part that I should talk about. Now, so far I've been talking about the representations of GB, but GF also contains fermion parity. So there is one more data that I need to specify. That is the fermion parity, which fully characterizes the representations of GF. So to characterize the interaction between the elements in GB with fermion parity, I introduce an index rho, which essentially characterizes the fermion parity carried by the representation of the bosonic symmetries. So it is defined in this fashion. If a representation commutes with the fermion parity, it has a +1, and otherwise it has a -1. And this is a group homomorphism. And such group homomorphisms are then characterized by the actually first group cohomology. Then what we should know as a mathematical background is that the projective representations of GF, which has such a decomposition, are characterized by a pair of indices, nu and rho, that takes values in the second group cohomology and the first group cohomology. And the linear or ordinary or trivial projective representation is then assigned the indices 0, 0. Okay, so this was the mathematical representation and mathematical background. Now, let me talk about two LSM theorems. So they have different setups. In the first setup, I actually think about only the case where the fermionic symmetry group is the fermion parity, and I don't demand anything more than that. And I consider the case of one-dimensional systems. Now, let's imagine that there are odd number of Majorana degrees of freedom at each repeat unit cell. Now, this kind of scenario may seem to be a bit unrealistic, but actually it can happen in certain critical systems that interpolate between topologically trivial and non-trivial phases. And for consistent definition of a global fermionic Fock space, I demand that I have in total even number of sites. So I have in total even number of Majorana degrees of freedom, but they are distributed in such that my translation repeat unit cell contains only odd number of them. And if that is so, I run into a trouble. And the trouble is that, well, first of all, even for this simple group, there is no well-defined local representation of the fermion parity. This is some sort of an anomaly. The global representation is well-defined. It is just given by the product of all Majoranas. However, you cannot define a fermion parity operator that anti-commutes with odd number of Majoranas, all of the odd number of Majoranas, just by the local Majorana degrees of freedom here. And how does this anomalous nature of the repeat unit cell, the local representation at the repeat unit cell appears? Well, if I impose periodic boundary conditions, what one can show is that the translation operator with periodic boundary conditions does not commute with the global fermion parity operator because the Majoranas anti-commute. And this then implies that there's a twofold global degeneracy. And this argument was first presented by these people. But now I will do something else. And this sort of is similar to the kinematic argument for the original LSM theorem. Now, this is not the only way to close the boundary conditions in a fermionic system. Another way to do it is to use the anti-periodic boundary conditions. This is essentially done by twisting the translation operator, but by fermion parity. And what I do is that I just translate every Majorana operator except the one at the ends, which are twisted by a minus sign. And then at this point, we lose the kinematic argument. Essentially, now the translation operator commutes with the fermion parity, and there is no obvious twofold degeneracy. Now, the question is that can we still somehow argue, even for the anti-periodic system with the anti-periodic boundary conditions, a constraint like the LSM or some sort of, can we make an argument for a degenerate ground state? And the answer turns out to be yes. And it follows in the following sense. So let's assume that I have a local Hamiltonian. I can construct any such local Hamiltonian by taking some object, a local operator that has some finite support, let's say, that is centered around the site 1, and I can continuously, I can keep translating it by 2n times, and I will get a translation invariant Hamiltonian. Now, let's assume that this Hamiltonian has a non-degenerate time gap ground state. And now I can construct another Hamiltonian. I can take this operator O, and then I can translate it by using the usual translation operator, which will now have periodic boundary conditions. Now, as I mentioned for the original theorem, there are two sides of it. The first argument will be energetic, and it's actually an assumption. Now, since O1 is identical in both Hamiltonians, the two Hamiltonians, first of all, differ only by a finite number of terms, because the twist only comes at the very end, at the link that connects the site 2n and site 1. So in the bulk of the system and in the thermodynamic limit, actually the two Hamiltonians are very close to each other. And if I assume that there's a spectral gap, then I can justify that if one Hamiltonian has a non-degenerate gap ground state, the other one would also have it. Essentially, a non-degenerate gap ground state would be insensitive to the change of boundary conditions. And this means that the Hamiltonian with periodic boundary condition must also have such a ground state, but this already leads to a contradiction by my argument, because the translation operator anti-commutes with the global fermion parity, and there is a twofold degeneracy. So that's sort of the way to prove, and this part forms the kinematic part, kinematic argument, prove the LSM theorem for a system of for a fermionic system where there are odd number of Majoranas at every repeat unit cell. Now we can do a little bit more than that. We can actually generalize it to. Is there a question?
Yeah, can I ask a question? We'll go back one slide.
Yeah.
So, I guess I understand point number 1, point number 3, but point number 2 with the energetic argument. How do you know that two Hamiltonians can be continuously deformed to one another?
Sorry, I can't, somehow I can't hear you well.
Oh.
Maybe it's because of the distance. So I think you didn't understand argument 2.
Yeah, argument 2. Why can you continuously deform them without closing the gap? How do you see that?
So unfortunately, I don't have a proof for this indeed. But let's say that the Hamiltonian with anti-periodic boundary conditions has a non-degenerate and gap ground state. Now I don't have a continuous twist operator, of course, and I cannot use a continuous twist operator to sort of adiabatically twist my ground state. But what I can do is that I can interpolate between this Hamiltonian and this Hamiltonian. I can simply choose a parameter lambda, and with the usual linear interpolation between them, I can multiply this with lambda and this with 1 minus lambda. Now, if the first Hamiltonian has a gapped ground state, the first Hamiltonian and the second Hamiltonian, they both have the same set of symmetries, namely they have a translation symmetry and they have a fermion parity symmetry. And if there's a spectral gap that is preserving me, protecting me, I just can, and since I'm not changing most of the bulk terms and just doing a very, very small finite number of change in the terms, I can assume that there is nothing going wrong if my ground state is unique. What can go wrong is that if my ground state is non-degenerate, changing some local number of terms may split this degeneracy. But if it is non-degenerate, you can also think about taking gap to the infinity, and somehow this, of course, this let's say a justified assumption. I can make the assumption that I can interpolate from one non-degenerate ground state to the other. But yeah. I cannot justify more than this, but with this assumption, at least I can prove, I can argue that there is an LSM type theorem that applies to both cases actually.
An assumption.
Yeah. It is. Let's say that it's an assumption that I don't know of a counterexample, and I don't have a proof. Unfortunately, yes, that's right. So it is at best an argument.
Operator modifying it when you translate is small because of one side basically. Could you argue that the one
The gap here is the same order as, I don't think there's a separation of scale between the size of the gap, size of the norm of these operators. I mean, just as an example of a system where the gap would close, like take like a topological superconductor in the ring geometry, and you can define it with zero flux and with high flux, right? And the ground state is zero flux or high flux at different fermionic derivations. So I think that means that if you try to interpolate from the zero flux Hamiltonian to the pi flux Hamiltonian, the gap will close. I mean,
I see.
Some crossing, right? There'll be a crossing because one state comes up in energy, one state goes down, and cross at some.
That's right. Yes, that is right, actually. But there's another. Okay, let me. I don't have any further justification for this, but there is another way of proving it, which I will come to it. Let's say. Yeah. Okay, then let me also make another assumption, and let me say that with the same assumptions, it can be generalized to higher dimension. But the way to do it is the following. Now, if I have a Hamiltonian with periodic boundary conditions, I can again choose a local operator, and it will have a translation symmetry that is a direct product of all these translation parts. And then I can just translate it around and then cover the entire lattice and construct the Hamiltonian with periodic boundary conditions. Now, it turns out that if I construct another Hamiltonian with tilted boundary conditions, and what I mean by is that essentially, let's say that this is a two-dimensional example. I am tilting along one of the boundaries such that if I go a cycle along the J1 direction, I essentially don't end up back, but I am going actually to the next site. So this is like twisting by a, okay, this is the tilting is essentially like a twisting by a translation symmetry. So if I go a full cycle along one direction, I actually translate in the other direction. And it also, this kind of argument also relies on the same assumption that a unique gap ground state must be insensitive to the change in the boundary conditions. And if you assume that, then you can show that actually with the tilted boundary conditions, there exists an algebra between the fermion parity and the tilted translation operator. And then you can show that you pick up a phase factor of -1 to the lambda -1, and lambda, by my assumption, is an even number because I must have even number of total sites to have a well-defined global fermionic Fock space, and I will end up with a minus sign. And then this implies a degeneracy for the tilted Hamiltonian, which must be also true for the Hamiltonian with periodic boundary conditions. Okay, so this is a simple argument, but let me just, without any proof, I will prove another theorem, and I will come back to this point, that any translation invariant local D-dimensional lattice Hamiltonian with odd number of Marion degrees of freedom that is invariant under both the translation and the internal symmetry group. So I can also demand some other symmetries, but here at least I demand at least the fermion parity cannot have a non-degenerate gapped and translation invariant ground state. And I also put an additional condition, short range entangled, because essentially when D is larger than 1, there also a possibility of a topological order that satisfy these conditions. And to characterize such a theorem, I introduce an additional index mu that characterizes the parity of the number of Majorana modes at every repeat unit cell. And if mu is equal to 1, then I say that there's an LSM type constraint that is preventing me to have such a gapped, trivially gapped ground state. Okay, now let me go to my second theorem. It essentially is the complementary. Now that I established that I must have even number of Majorana degrees of freedom to have a gapped ground state, let me ask the other question. Let's consider a system where there's a translation symmetry and there are even number of Majorana degrees of freedom at every repeat unit cell. And then I can consider the case of, essentially I'm considering the case of mu equal to 0. And at this point, I'm just assuming that GB is a discrete and abelian group, and that it is represented unitarily, which I will show why that is needed. And then I construct a global representation of the fermionic symmetry group without loss of generality as taking the product over local representations. And as I mentioned before, the data phi that characterizes the projectiveness of the local representation can be split into two parts. So it's a collective index that specifies the local projective representation. Okay, then it is sort of a generalization of what I mentioned. Now, instead of imposing periodic or anti-periodic boundary condition, which can be thought of as a twist by fermion parity, I'm now imposing a boundary twist by an element from the group. And if I do so, I can essentially prove the same theorem in 1D and higher dimension by looking at the projective phase coming out of it. The idea is that twisting the boundary conditions is essentially changing your translation symmetry. So you define a twisted translation symmetry by multiplying your translation symmetry by a local representation. And your Hamiltonian with periodic boundary condition is similar to the Hamiltonian with twisted boundary conditions. Then you can show that there exists a phase factor that is emerging from your global representation and your twisted translation operator. And one can show that this phase factor is 0 if and only if the local representation is trivial. And then whenever this local representation is non-trivial, there's a phase factor and you run into a contradiction. Okay, so this is the proof in the same fashion. And I restricted my symmetry group to be unitarily represented and abelian because I wanted to make a twist here. Well, if it is an anti-unitary symmetry, I don't know exactly how to do a twist that only changes intensive number of or some finite number of terms, because complex conjugation in principle acts on anything. And for a non-abelian group, once you do a twist, you cannot have invariance under the whole group. You can have an invariance under some conjugates class. Perhaps the similar theorems can be applied, can be proved by using similar arguments, but I did not do that. Now there exists if I restrict to one dimension, there exists a proof of this kind of statement on any for any group. And let me sort of sketch that. Let me first state it. So if I have a one-dimensional lattice Hamiltonian that is local and it has a global symmetry group translation and some internal symmetry, and I assume that my fermionic symmetry group decomposes, then I cannot have a non-degenerate gap ground state if the local representation of GF is non-trivial, has a non-trivial projective representation on every repeat unit cell. Now the proof of this statement is actually, so for a general GB that can be unitary, anti-unitary, or non-abelian, the proof utilizes the so-called fermionic matrix product states. They come in two ways because you want to specify the fermion parity of the ground state. And well, if you are familiar with the usual matrix product state notation, you assign to each side some virtual vector space, and then you essentially assign a matrix that is acting on a virtual Hilbert space, and then you essentially contract these matrices to construct your states. Now there exists a very special type of in one-dimensional world, there exists a special type of matrix product states that are called injective matrix product states that have some certain well-behaving properties. It turns out that they are good at representing the non-degenerate gapped and symmetric ground states of one-dimensional local Hamiltonians. And if that is so, then what one can do is that let's assume that there exists. So, okay, the proof assumes that I have a even fermion parity matrix product state, and it can be also generalized to the odd case. assume that my ground state that is non-degenerate gapped and symmetric can be approximated by an even parity fermionic matrix product state. Then it turns out, well, if it is symmetric, then I can write it as a singlet state under my global representation. But then it turns out that because of some nice properties of the matrix product states, actually you can compare the U of G times U of H with the U of G H. And what one can show is that actually the projective phase of the local representation, you can pick up the projective phase of the local representation. First, you can show that this condition holds, which is like a co-boundary condition. And then you can also show that this equation also holds at a local level. So you can replace the global representations U of GH and U of G and U of H with the local representations. But that is nothing but the co-boundary condition for the projective phase. Then you can conclude that your indices, local indices, must be 0. Now this is so in 1D, by using matrix product states, one can make the general statement for the general proof for the theorem 2. And once you have this proof, actually you can go and, for at least in 1D, you can also prove this theorem 1 without assuming this tilting and twisting idea. What you can do is that you can assume that there exists such a non-degenerate and gapped ground state, and then you can show that if you take such a ground state, the tensor product of such a ground state with itself, it describes the non-degenerate and gapped ground state of a Hamiltonian where theorem 2 applies. And then you can show that actually by theorem 2 you cannot have, so your initial assumption of a non-degenerate gap ground state was wrong. And so from using theorem 2 you can also prove theorem 1. Okay, so in 1D at least I have a more rigorous proof. Unfortunately, I don't have a proof for the shortcomings in higher D by this tilted and twisted boundary conditions. And I'll think about the example that you mentioned. Okay, so these are the two results that I wanted to first present. So just as a summary and recap, I introduced triplets of indices which characterize the LSM theorems in 1D that applies to fermionic systems. And the zest of it is that if this triplet of indices are non-trivial for each repeat unit cell, with a translation symmetry, you have an LSM type constraint that prevents a non-degenerate gapped and symmetric ground state. Then actually out of these indices, if you remember, the nu was characterizing the bosonic part of the symmetry group. So actually nu also contains the similar kind of bosonic LSM theorems that relies on local projective representations. And then whenever rho or mu is non-trivial, these two indices are only associated with fermionic systems. And the LSM theorem is, so to say, intrinsically fermionic. It cannot be realized in models with strictly bosonic degrees of freedom. So that's the first part of the talk. If you have any questions, further questions, let me know. Otherwise, let me switch the gear and talk about something else. I'll talk about the systems with LSM theorems and certain dualities in 1D. And the motivation comes from the deconfined quantum criticality the deconfined critical points in one dimension. So the idea is that let's say that we have a Hamiltonian with G symmetry, which has two subgroups, G1 and G2, but neither G1 nor G2 are a subgroup of the other. And then if a deconfined quantum critical point describes a continuous transition between two ordered states that break these distinct symmetries. So it's also called a non-Landau-Ginzburg type transition because it's not from a symmetric state to a symmetry breaking state. The two states break distinct symmetries at some point in the parameter space. Okay, with this motivation, there's an idea of a mixed anomaly of two symmetries, G1 and G2. And there are many ways of stating this and formulating this. But one way of doing it is that if there is a local Hamiltonian with G1 times G2 symmetry, has a mixed anomaly of this symmetry, then such a Hamiltonian cannot have a non-degenerate gapped and G1 times G2 symmetric ground state. and this is reminiscent of an LSM theorem. If you replace one of these symmetries with translation and the other one with the internal symmetry. So LSM constraints can be interpreted as a mixed anomaly between spatial and internal symmetries. And the motivation for this project is to understand better this statement, what it means, and understand it from the point of view of a deconfined quantum criticality. Okay, so in the second part, I'll talk about certain non-Landau-Ginzburg type transition, which is due to an LSM anomaly, and I can map it to a Landau-Ginzburg type transition. And the model that I consider is actually something well known. So I wanted to start with something for which I know the phase diagram. So I will consider the anisotropic J1, J2 XY chain. So this Hamiltonian has only sigma x, and sigma y coupling. Delta characterizes the anisotropy, and there is also a next nearest neighbor coupling, which is due to the J. Well, J is roughly speaking the ratio of the J2 to J1, and then I normalize my Hamiltonian by J1. And in the parameter space that I will consider will be delta larger than 0, and J is between 0 and 1/2. Now, this Hamiltonian has many symmetries, but for my purposes, I will only focus on a certain subset of them. First, the internal symmetries are the pi rotations along the x and y axis. So this is Z2 times Z2 symmetry, and they act in the usual way. And my spatial symmetries are, actually, I will consider two of them. One is a translation of 2n sites. I restrict my total, I consider total number of sites to be even, so that my total spin number will be an integer. And then the other spatial symmetry that I consider is a reflection that is site-centered. So in particular, under this reflection symmetry, there are two sites that are mapped to itself, namely 2n and n. Okay, for this system, there are two LSM theorems that apply at the same time. First, a T-repeat unit cell, this internal symmetry is realized projectively. So this is like the LSM theorem that I described to you. And the way to see it is easy. For a Pauli operator, we have sigma x and sigma y anti-commuting. And then there is also a generalized LSM theorem, which I did not prove, but it has been proved in various places, that at each reflection center, there exists a projective representation of this group as well. So these reflection centers are the site n and site 2n. And the statement is that, well, they apply separately, that there is no gap ground state that is symmetric under internal symmetry times translation or internal symmetry times reflection symmetries. Okay, and that is indeed what we will see in the phase diagram. So in the J delta phase diagram, I have three gapped phases.
Sorry. How are the reflection centers different from the normal sites? Like, if the projective representation applies for every site, wouldn't they also apply for n?
Sorry, can you get a bit closer? I can't. Sorry.
If the projective representation occurs on every site, then wouldn't it naturally also occur on site n into n?
That is right, actually. Indeed, that is true. One can somehow deform this system to not have the translation symmetry, but you can still preserve the reflection symmetry by making these couplings site dependent, so to say. But even then, the LSM theorem still holds. And the reason why I'm thinking about reflection symmetry will be more apparent in the coming slides. But you are right. Of course, once you impose a translation symmetry on any lattice, depending on the translation symmetry you impose on the lattice, you will have certain set of spatial symmetries that come together. That's true. Yeah, I think that's the short answer. Now the phase diagram of this Hamiltonian has three gapped phases. There's a Néel order in the x direction and Néel order in y direction, and there's also a dimer phase. So actually, if I set J, I think it's easy to see. If I set J to 0, my Hamiltonian is just described by nearest neighbor antiferromagnetic coupling. And at point delta equal to 1, I retrieve the well-known XY model, which is critical. And each of these gapped phases actually break distinct symmetries. So nil X and nil Y phases break only the internal symmetry while keeping the reflection symmetry. All gapped phases break the translation symmetry of two n sides down to n sides. And then dimer phase preserves the internal symmetry while breaking the reflection symmetry. And there are continuous phase transitions between them, and all of the continuous phase transitions are deconfined quantum criticality. And in particular, the delta equal to 1 line is well known. All of the lines are described by C equal to 1 compact boson theory. And there are two maybe special points in this vertical line at delta equal to 1, namely, so this compact boson theory has the fields in the compact boson theory has the compactification radius of square root of eta over 2 and the square root of 1 over 2 eta. And at this point, when j is equal to 0, we retrieve the free Dirac theory for which eta is equal to 1/2, and compactification radius becomes 1/2 here. And here eta is equal to 1, for which the compactification radius is 1 over square root of 2, and that has an emergent SU2 symmetry, and it realizes SU2 level 1 CFD. Okay, so this phase diagram we know, but what I'm going to do now is something else. I will do a Kramer-Svenier duality, but I will do by gauging a symmetry, the internal symmetry of pi rotations around Z, and that's the diagonal element of this group. And how I do it? Well, the standard procedure is to introduce additional degrees of freedom at links. So I denote them by tau x, tau y, and tau z, and I impose a Gauss constraint. So the Gauss constraint is implementing the symmetry sigma z symmetry locally, and it is decorated by my gauge degrees of freedom. So it's a gauge field in the boundaries, and I will impose the Gauss operator to be 1. And now I can construct a Gauss gauge invariant Hamiltonian after minimal coupling, and the way to do it is that both sigma x and sigma y are odd under sigma z. So I put for each link a tau z operator, so that now the Hamiltonian commutes with all the local Gauss operators. Okay, now the next step is to actually define some unrestricted and gauge invariant variables that satisfy the Pauli algebra. And how I do it? Well, tau x operator already commutes with the Gauss operator, and I also constructed tau y and tau z, but they need to be decorated by the physical degrees of freedom. And this way, essentially, I'm reducing the extended Hilbert space into back to its original dimension. And in terms of these variables, I reach to a Hamiltonian of this form. And this is effectively the Kramer-Svenier duality applied on my original Hamiltonian. And you can notice several features of it. First of all, if I set j equal to 0, it describes the paramagnet where I have a single z for delta equal to 0. And for that very large delta, this describes the so-called spin cluster model, which is actually an SPT phase. Okay, so this is my Hamiltonian. Now I want to also look at what happens to my symmetry operators that I mentioned. Now I want to construct dual symmetry operators that are also locally gauge invariant. What do I mean by it is that, so my Rx operator before was just the product of sigma x's, which implement the pi rotation around the x-axis. Now I pair them since I had two n sides, and for each pair I insert a tau z operator so that locally this operator also commutes with the Gauss operator. And in terms of my effective degrees of freedom, what I found is that actually the representation of Rx in the dual picture is only the z operators acting on odd sides, and it doesn't act on the even sides. And for Ry operator, what I found is actually the same operator again. So it is again the Z operators that is acting on the odd sides, and that's expected because I gauged the diagonal element of the Z2 times Z2. And the RZ becomes, since I impose Gauss constraint to be 1, RZ becomes 1, which is also the product of the two. And now I also have a dual symmetry in the dual model, which is generated by the product of tau Z's. But to make it locally gauge invariant, I decorate it with sigma x's. And then now it is acting as Z on all of the sides. So the product of the RZ check, the dual symmetry together with Rx gives me the Z operator on the even sides. Okay, so these are the internal symmetries, but what happens to the spatial symmetries? Now, under the on the local degrees of freedom of the dual system, the translation operator acts as in the usual way, but something interesting happens to the reflection operator, and it is not hard to understand because effectively by introducing this x, y, z operators, I went from local degrees of freedom that I defined on the sides to local degrees of freedom that I defined on the links. And what happens is that now this reflection operator that was side-centered before is now link-centered, essentially. And it does not, in particular, there is no side J that is invariant under this symmetry operator. So each side is mapped to one another. And more interestingly, what happens is that because of this new feature, the algebra of the global symmetry is changed. It is not a direct product anymore. But for instance, if you conjugate Rx by translation, it was Z operator on the odd sides. You actually get Rx times R check because now this is the Z operator on the even sides. And similarly, by the same logic, conjugating by the reflection symmetry, essentially changes the Z operator on the odd sides with the Z operators on the even side. So what happens essentially is that after imposing this, after applying this duality by gauging the internal symmetry, I get a mixture of the internal and the spatial symmetries. And the mixture comes in both ways because my internal symmetries are now acting differently on even and odd sides. And for that reason, it is mixed with both translation and the reflection symmetry. Now what I will do is that since my original, in my original phase diagram, all of the phases were breaking the translation symmetry, I will actually forget about the translation for the time being, and I will focus on the internal symmetries times reflection. And I look at the phase diagram of this Hamiltonian, and what are the phases that it breaks and what are the phases it does not. Now, if I throw the translation symmetry, actually the group of the internal symmetries together with the reflection is the group D8 dihedral group. What happens is that the nil X and nil Y phases are mapped to a trivial phase, a trivial gapped phase with D8 symmetry and then SPT with a D8 symmetry. And the confined criticality between them is still a non-Landau type in the sense that it's a topological phase transition. But the nil X to dimer transition, which was the confined critical, is now a usual Landau-Ginzburg type transition where the dimer phase is mapped to a trivial phase with a partial symmetry breaking, and it only has the Z to X symmetry. The transition is just a symmetry breaking type. Whereas the nil Y to dimer transition is actually a combination of two. It's a non-Landau-Ginzburg type, and then together with a topological transition, so to say. Okay, with that, let me state, so this is my final slide. Let me state some general lessons that one can notice from this exercise, and stay tuned for an upcoming paper. So non-Landau-Ginzburg type transitions can be mapped to Landau-Ginzburg type transitions. This is sort of already known for several internal symmetries and so on. And the way to map it is through gauging related dualities. Now, if you have an underlying LSM constraint, which is a mixed anomaly of the spatial and internal symmetries, doing this costs you to mixing the spatial and internal symmetries. So that's how in this exercise, how the mixed anomaly manifests itself. The group algebra changes after applying the duality. And also in the dual model, LSM constraints disappear after gauging the internal symmetry. It is easy to see it because the global representations, first of all, have the local. So the local versions of these global representations are just Z operators, which commute. So the local representation is trivial. And the second reason is that the side-centered deflection becomes link-centered. So the generalized LSM constraint also does not apply to this system. Okay, with this, I thank you for your attention. And if you have any questions.
Maybe I can start with one question. Can you hear me?
Yeah, sort of, yes, a little weak.
So if you go back to your phase diagram, maybe it's one slide back.
Yeah.
So under this mapping, you were able to take one of your deconfined quantum critical points and map it onto a Landau-Ginzburg type transition. Are there other mappings that would allow you to do that with the other transitions? Like you have three types of.
I see. So you are asking if I can make each of these boundaries Landau-Ginzburg type, essentially.
Yeah.
So the answer, I don't know on top of my head, but it is probably true by essentially, because there must be, well, there's a reason for why this transition becomes Landau-Ginzburg type, and there's a way to see it not from the microscopic procedure that I did, but looking at certain topological partition functions and their anomalies. And I guess if you so your internal symmetry has three generators, well, two generators and the diagonal element. So depending on which one you gauge, essentially, you should get different boundaries. And another way to get, so this is one, okay, so Kramer-Veniers is one duality that you can apply in 1D. The other duality is also Jordan-Wigner, which you can also induce by gauging your internal symmetries. And my guess is that depending on which of these Z2 symmetries you gauge, you will get a different boundary here that becomes Landau-Ginzburg type, and the others will be necessarily, I think, between an SPT and trivial phase. At least this is what I'm expecting.
No more questions. Let's thank Omer again.
Yeah, thank you.
One more question about that, the point in the middle where all the three lines meet. What's understood about that point? Is that some kind of tri-critical point? Or?
Yes, it is. Yeah, it is. It's a multi-critical point in the original phase diagram. It has an emergent. Yeah, it's a special point because it's an emergent SU2 point, and it still persists. So it becomes a line if you introduce one more anisotropy for the ZZ coupling. Here I'm just looking at one face essentially where there's no ZZ coupling. Now the question here, what happens here for this point? It still appears to be an SU2 symmetric point. Although I don't have a well description for this point at the moment. Yes, it's also something that we should look for. Yeah. And it's another tri-critical point. Yes, it would be interesting to understand this on general grounds.
Would it be like some orbifolded version of the SE2?
Sorry, Caroline, I couldn't hear you.
Okay. Would it be like some orbifolded version of the SU2 level 1?
Yes, that is right. Actually, yes, you are right. It is so this gauging in particular at the CFD site is exactly orbifolding. It gives you the orbifold theory, and what happens is that this theory has compactification radius 1/square root of 2, and it turns out that the orbifold theory also has the same compactification radius. Also, it would not be the same for other points, but you are right. Then essentially this line exists on the orbifolded theory, and I'm not, these other two as well, but I'm not very sure about their compactification radius actually.
three indices that you wrote for the fermionic LSM theorem, are those like related to the three indices to find like two?
Yes. That's also another thing that I am sort of working right now. And yeah, I don't know the answer. So what I can say is the following. Okay, so I had these three indices. So first of all, I know at least one case where mu appears, and it's actually a critical theory. If you consider the transition between the non-trivial and trivial phase of class D, so Kitaev chain, it indeed in the criticality has a translation symmetry for which there's a single Majorana at every site, and that has a mu equal to 1. So this LSM kind of theorem applies, and it has a gapless spectrum, so it is consistent. And that is also, so it's a Majorana C equal to 1/2 CFT, but it also has a global supersymmetry actually, because your translation operator does not commute with your global fermion parity operator. Now, I don't know if these properties persist for rho equal to non-zero, or in general, if it persists for other type of indices or mixture of them as well. That's something for investigation, further investigation. Also, you're right. Essentially, here I'm just thinking about a spin system where there is no fermionic LSM theorem applying. So I don't know what would be the additional features of a fermionic criticality, essentially a deconfined criticality with fermionic indices, fermionic LSM indices.
Thank you very much. Thanks for the talk.
Yeah, thank you for having me.
Thank you.
Bye.
Bye.